Well, thank you very much. So I will also talk about corals, but these corals are actually underneath. What you see here to the left here is a false color image of the sea surface temperature around the Bahamas and the North and the Atlantic. And basically, every dark color is where the warm surface currents flow in the seaways, especially in the Straits of Florida. And beneath these currents is a hidden ecosystem with it's incredibly beautiful and incredibly abundant, and I want to show you that today. So a lot of cold water corals down there, and to the right here on the first slide, you also see many of the people who contributed to this research. One of them, Shirley Pomponi, who dives with us onto these wonderful reefs. So if we pull back the currents and look down into the riverbed of the Gulf Stream, and you see all the red dots, that was in the 70s. Cairns looked at dredge samples and found deep water corals in all these positions. Later on, of course, a lot of the submersible dives, Chuck Messing, Shirley, John Reed, Conrad Newman, they have found many of these cold water coral mounds down there. And just for people who not quite familiar what the difference it is between the cold water and the shallow water corals. So the shallow water corals, as you all know, they need light because they have the little zooxanthellae in their tissue that provides them the sugars and the energy for life and are sort of the crucial portion of that whole symbiosis, and it also makes them pretty vulnerable to shallow water corals. The cold water corals, on the other hand, they like it cold and dark. So they live in about 200 to 1,500 meters. They have very nice aragonitic scleractinian corals with mostly branching forms and pretty sturdy. But they have all types of different species. On the last cruise we identified over 30 different species on the slope of Great Bahama Bank. They also form big mounds, and this is on top of a 120-meter big mound, so big coral reefs, where you see a beautiful Ophelia pertusa coral head or bush with crabs in it and fish with it. So they are really in temperature of, here you see 7 degrees Celsius, normal salinity seawater, beautiful coral reefs. So what do they live from? Well, here you see just the delicate structure of some of them, but what I want to make sure that you pay attention is to the background on all this. It looks like snowflakes coming down through the water column. And this is the reason why we have so many corals in the Straits of Florida and in some other seaways in the Bahamas is that the currents above it, they bring all this sediment, but also a lot of particulate organic material that then comes down and gives the food to these corals because they're heterotrophs, they need to eat. And how do they eat it? Well, their structure is so that they actually have like little hands that go out and they catch in the dark this particular organic matter that provides them enough food for a living. Well, the corals are not just the only ones down there, it's a whole ecosystem. And here we see a fish that came in about 200 million years ago and has not really evolved much, is part of the system down there, but many other fish, squids like this one here, that floated by. And then, more importantly, for many other researchers are the sponges, and Shirley will talk about these, all different types of sponges. Some are really silica-rich sponges, and many of them, they have compounds that can be extracted for medication. And the cruise where we went on, actually Shirley investigated several of these beautiful sponges. So just like the shallow water coral reefs, they actually form mounds. And the way they do this, they start somewhere, settle, and start a colony. But because they're down there, they constantly get sedimented in, so they trap the sediment in between, and they grow above it, and they just pile up on top of each other till they reach pretty high mounds. The largest one we found was 120 meters high. So sort of we have known all this for many years. What was not known is really the distribution of these corals. And if you go down with a submersible or just with you go and have a sort of a spot observation, but not really a spatial one. So in 2005, we decided to go and look at this with the geophysical tools to look if we can actually map these habitats. And the first grant we got was with an AUV going down, and this AUV up on the right is like floats 40 meters above the seafloor and takes all type of geophysical instrumentation on it. Then a year later, together with Shirley, we could actually go and ground truth the geophysical data. Later on, with the French crews, we mapped large areas north of Little Bahama Bank and to the west of Great Bahama Bank. And in 2012, went back with an ROV with the German vessel to ground truth that data set. So let me first show you from the beginning again here this autonomous underwater vehicle that flows independently above 40 meters above the seafloor and has a whole array of geophysical equipment in it. So the multibeam for the depths, backscatter imagery for the seafloor sediment composition, has an acoustic Doppler for the current salinity, and all this could be measured. And the resolution is about a meter of topography. And you see here at the base of the Miami Terrace, the ridges and notch. So on the right-hand side here, you see a sand wave field. Here we have an undercurrent from the Florida current that flows south and makes a sand wave field with crossbed and ripples. You would think you would be on a shoal in the Bahamas. Up towards the Miami Terrace are all these ridges. And all these ridges are actually perpendicular to the current, and they're slightly asymmetric. What you also see in black and white here, draped on top of the topography, is the backscatter imagery. When we zoom in a bit, we see that all these ridges are slightly asymmetric. They are a bit steeper to the north. They have a white trough in between and have a dark crest. And then with the crews with John Reed and Shirley Pomponi, we could actually calibrate this backscatter data, and we learned that the white stuff, or the white backscatter, is the mud, where it's really soft mud, and the crests where we have to do the dark backscatter, that is where the standing dense corals are. And so we were able then to map out on this whole Miami Terrace all the coral coverage, and here you see the habitat mapping here on the foot of the Miami Terrace with 4,600 patches of standing corals, dead or alive. If we go now across the strait, first in the middle of the strait, and then to the north-south transect on the foot of Great Bahama Bank, you see the topography or the seascape changes quite a bit. In the middle of the straits, it is up here, we see the middle of the straits, it's more a knobby. To the right, it's more like pointed big mounds. And if we go now to the middle of the straits, you see it's like an elephant skin. Here the hills are up to about 40 meters high. They have but it's all knobby and has sort of a chevron-type pattern. When we drape again the backscatter on top of it and the track of the submersible with all the different sediment surfaces, then you see that again, all the black patches are actually coral patches, the dense coral patches. So the whole seafloor down there is basically covered loosely with corals. And they make a topography, a seascape, that is several meters high throughout the whole Straits of Florida. When we go over to the off Bimini now, the seascape changes completely. Here we have these long linear ridges, much higher features, but also less knobby and all that. The highest one is the one on the second ridge, and we called it the Matterhorn. So the Matterhorn has a steep northern slope and is 120 meters high. When we went there with the submersible, it was really from top to bottom covered with corals. You see very nice, all the standing corals, some dead, some alive, and in the background you see the white sediment surface that is trapped between the corals. And that is really from the bottom all the way up 120 meters. With the French crews, we went back and we took two cores, one to the right of the mound and one in the mound itself. And we penetrated 7.5 meters with a piston core, and it was an alternation of coral rubble and sediment, just as we would have expected. When we dated this, so we had some samples from the top that we collected coral rubble during the submersible cruise and on the foot. So it was 300 and 600 years old. And then the core, a meter down, was already 16,000 years. And 5.9 meter down was nearly 500,000 years. And then it went below the age dating methodology of uranium thorium, so it's over 500,000 years old. And the knobby, the way this pointed topography persisted all along on the Great Bahama Bank side. Not quite always that high. The one on the bottom and the side one was 70 meters, the highest one. The interesting thing is that when we look at this, we have quite a bit of, all these big mounds have beautiful coral coverage on the top. It was just luscious growing corals, whereas in the more subtle topography in the middle of the Straits and on Miami Terrace, the coral coverage was never quite as rich as on these ridges. But what was interesting is if you go back to what makes the topography of these mounds. Well, people have shown before that some of the mounds in the Straits are actually elongated because the north-flowing current makes this teardrop shape. When we looked at along the slope of Great Bahama Bank, there was absolutely no preferential mound orientation. It went in all directions, and we could not explain this correctly. If we realized the current switches back and forth every 6 hours. It's like an internal tide at the bottom, and so we thought maybe that's because we have such a crazy current system down there, but actually we could not really explain it. And we only could do that after we did the slope morphology together with the French crews, where we went 180 kilometers from north of Bimini all the way down to close to Quezal Bank. And we look at two areas. Up north, just off Bimini, the whole slope is like a channelized slope. It looks like an underwater river valley with large boulders in it. Further south, we have a lot of slope failures, and the largest one you see at the bottom there were about 72 square kilometers of 7,200 square kilometers of slope shifted away. With the Germans, then we went and investigated that, and what we found indeed up north of Bimini, we had a coarse slope with a lot of life there, a lot of sea urchins, dead and alive, and we saw the boulders and the currents with the wave sediment around it, and the boulders were covered or colonized by corals, sometimes partially covered and sometimes completely covered. And these boulders underneath the corals that are really a wonderful foundation and for a hotspot of the coral growth. If we go further south, we had this submarine landslide in the Straits of Florida. Must have produced a nice tsunami over in Florida about 200,000 years ago. And we know the big slab that is up front is about 2 kilometers long. And we took a piston core on top of it and has a beautiful coral carpet on top of it from the deep water corals. But even some of the boulders that were further back, they start to be colonized by the corals and all different types of organisms. If we go further south, we had an old debris field, and this field had the largest one, and this field was what we called the Twin Peaks. And when we went with the submersible, like the Matterhorn, it was covered on all sides with beautiful corals. However, when we tried to take a core through it, we produced a banana. We tried twice, and we just bent the pipe. So there must have been a boulder underneath, so the whole block is basically a boulder, and so it's just covered by corals, but not the whole mound is coral. So we found all type of things then. We had the boulders with some coral growth, with a lot of corals, and of course coral rubble with all that in it. So along the Great Bahama Bank, a lot of our water corals actually sit on boulders. They use that to colonize with the larvae. So you could say they're really on boulders, but they're incredibly beautiful. And to the end, I want to show you a couple of these pictures that are just wonderful. They were taken by the ROF by the German cruise that we did in 2012. So some of the corals, and then we have all the different types of organisms on it, with the sea urchins, with sponges, with every different types of corals. As I said, over 30 different coral species were identified. The fish that are on it, and sponges. In this one, my student says she identifies 16 different species just in this picture here. It's just a highly diverse ecosystem down there. It's incredibly beautiful. So why should we care? Well, it's a thriving deep water ecosystem of unbelievable beauty. And it's really hotspots for biological diversity all along in the seaways of the Bahamas. and they provide a habitat for different organisms, included commercial imported fishes, and as Shirley will show you, also they supply compounds for life-saving medication. Well, there are also some dangers, and just like in the shallow water environment, the fishermen are the culprits to some extent. They go out there with their fish finders, they find one of these mounds, and they start fishing, and they fish out all these beautiful old groupers, some hundreds of years old, and they're so proud and happy that they have fished out the whole coral mound. All the fish are gone in one afternoon. And of course, we also have other dangers. That was over in the Gulf of Mexico, the big oil spill. We were always afraid that the loop current will eventually bring part of the spill over. Luckily, it didn't happen. But over in the Gulf, of course, all this sinking oil actually destroyed quite a bit of the cold water corals in that region. And the little brittle stars that they go into the one coral and stay there their whole life, they're still in there, but the coral is actually dead. And so with that, thank you very much.